But I want to spend a few minutes with you folks, kind of getting you thinking about systems. It's our next unit. Now, maybe you're saying, oh, okay, hey, I remember systems. Cool. We're going to add a lot to it. Or maybe you're saying, oh, I'm not sure. Do I remember systems? Well, that's what that half sheet of paper is trying to do, is just get you back in the swing of things. Let me say this, no matter what you're thinking, we're not going to be solving systems like for the next 3 weeks just for the sake of solving systems. We're going to solve them for the next day, and then we're going to end up applying them to all kinds of things. And that's a lot of how the second half of the year works. We'll take a look at some ideas that you've seen, and then we'll apply them in new ways. Now, at the top of your little half sheet of paper, I almost wondered, should I write this again? But I did. But we just said this the other week with polar systems, right? So just don't forget that the solution to a system is a point. It's a point of intersection. Again, you probably feel like you've heard that a few times. Now, we have different ways to solve a system. We have a graphing method. We have a substitution method. We have what's called the elimination method. I'm not going to make you write an essay about those methods, but can you use them? And I don't really care what method you use, but when you look at letter A or B or C, is there something that sort of comes to mind, a good method for solving them? I want you to spend a few minutes and see if you can get back in the swing of things. There are some hints on the back. Let me just say, it's okay to look at them, but look at them at the right time. Don't look at it right away, but do look at them maybe to see if you're on the right track. So it's okay. Look at the hints, but just pick a good time to look. And let's see where we end up with the next few minutes with these 3 problems. Looks like we're off to a good start with letter A. So how about letter B? Letter B. Keep working if you're good, but if you feel like you need something, if you multiply letter B by 100, if you basically multiply both equations by 100, well, it becomes more normal. Assuming the definition of normal is that you get integers. So something to consider. It's 100% legal. You do need to then continue to change so that you have opposites. Most of you did, and you're good, but you could multiply both equations to get the y's as opposites. So you multiply by 4s and 5s. Okay, that's going to give you a version of the equation where the y's become 20s and some other values change. Particularly if you can't find your mistake, maybe just double check that everything got multiplied by 4 and 5. It's not the only way to do it. Sometimes people will multiply by 3s and 2s. If you multiply by 3s and 2s, then you're going to make the x's become opposites. But you are going to need something to be negative. Maybe you'll multiply by -3. Okay, you don't have to do it both ways, and I have seen some other variations, but we would end up, again, with the x's being opposites if you multiply, positive 208. It does work out either way. Did you get it to work out to be 16 and 14? 16 and 14. Now, maybe it's good if you didn't get letter C to work out, or if you notice something a little strange about letter C. Okay, I was wondering if you would do a substitution method. You don't have to substitute, but It seems like it's ready for that. But the x's cancel out. Yes, the x's cancel out. You end up with maybe 2 equals -6 or 0 equals -8, depending on kind of the route you went. Okay, now, as I saw some of you do, which is good, you say, oh, that's no solution. Now, that is correct. It's no solution, but we want to be careful that we don't just quickly yell no solution just because, quote, everything canceled out. Okay, actually, the reason it's no solution has a little bit more to do with the type of result. In other words, we actually end up with a false result. 2 does not equal -6. 0 does not equal -8. When you get a false result, then you say no solution. Actually, I'm going to compare that with, or contrast that with, a true result. Okay, it's actually not a problem that you did yet, but just stay tuned if you don't mind. I'm going to show you something that's actually kind of the opposite. A few more things on this just quick intro day. At the bottom of your paper, there's some classifications. Maybe you have not heard these words. It's not a big deal. They're just some vocab words. We're not big on vocabulary, but I've seen these words used in some higher level math. And they're just some fancy words that describe some concepts you've been around. So I want you to get comfortable with the idea of a consistent system. Consistent. A consistent system means that it has a solution. Okay, now a lot of the problems on the board are consistent because they have a solution, but there's actually a subcategory, independent and dependent. Look at the detail. Independent means exactly one solution, and then dependent means infinitely many solutions. Okay, in a second, we're going to go back and classify what we just did, and I'll show you how to use these words. You might not use them in a conversation with a friend, but we can use them when we talk about systems. The other situation, as you see on your paper, is an inconsistent system. Inconsistent, well, that's the one that has no solution. So, as honestly a simple exercise, just so you get the idea, if I was going to classify system A, it had exactly one solution. It was that point. Boom. Well, that means this system is consistent and independent. Consistent and independent. You use both words. If you don't want to use the word and, you would just say it's a consistent independent system. It's a consistent independent system. Honestly, likewise with letter B. It's a consistent independent system. Now, are most systems consistent independent? Probably, because most systems, we get a nice little answer. But let's make sure we understand a few other things up here. Okay, because this no solution system, yes, it's the inconsistent letter C. Letter C is inconsistent. It's just kind of another word for the same idea, but it's inconsistent. But just kind of think back to basically the basics of algebra. Probably the first time you did one of these in Algebra 1. Remember, the solution is an intersection point. So what does that mean about letter C? Well, it means, of course, that there is no intersection point. Of course, they would have to be parallel lines. So again, letter C, if we were going to graph it, we would be graphing parallel lines. And it reminds me of the little parallel line joke that's hanging up on the bulletin board across from the water fountain. Does anybody ever stop and read those? I like the parallel lines joke. Parallel lines, it's so sad. They have so much in common, yet they'll never meet. Okay, so, but that's what makes them inconsistent. What am I getting at? I'm trying to get at the one we haven't done, infinitely many, because sometimes people are like, what do you mean infinitely many? This intersects at one point. This intersects at no point. So what would it mean to have infinitely many solutions? It would mean that they would intersect at every point. Wait, what kind of lines are going to intersect at every point? Let's make up a letter D. Let's make up a dependent system. Okay, you put it somewhere, maybe at the bottom, maybe on the back. What kind of lines would intersect at every point? Here's a line. I'm just kind of making up a line. No big deal, x plus y equals 5. What kind of line, or maybe I'll say what would be another line or another equation that would intersect that at every point? Okay, it's weird, but the answer is the same line. The same line. If I graph that line and then I graph that line again, yeah, it's going to intersect at every point. Now, let's try to make this as fancy as possible. Let me give you an equation that is in disguise. It's the same equation, but it's in disguise. It's not a tricky disguise. You know, like 10x plus, or 2x plus 2y equals 10. Again, it's not a tricky disguise. It's the same line. Make sure you understand it's the same line. Now, if you didn't recognize it, pretend that you don't recognize it, and you went to solve this, I hope you would try to get opposites. -2 seems to be the number, the magic number. Now, if you multiply by -2, because you're trying to solve this, then you might be like, oh, wait a minute, everything's going to cancel out. But here's kind of the main thing. Like I said a few minutes ago, just because everything cancels out, don't throw your hands up in the air and say no solution. In fact, it's the opposite. Because this is a true statement. Because this is a true statement, it actually would say infinitely many. Infinitely many. Or using kind of the fancy words, consistent but dependent. Consistent but dependent. In case you just need it kind of driven home, the only way you're going to get a consistent dependent, the only way you're going to get infinitely many is if you have the same two lines. Again, it's kind of strange. You usually don't. But if you did, you would get a true statement. 0 equals 0. 5 equals 5. Whatever is true. Okay, but please don't say no solution. Technically, they are opposite.